Welcome to part 2 of our emissions on the vehicle. We're going to pick up right where we left off, and that is we're going to talk about the EVAP system. EVAP is not an acronym. This is short for evaporative emissions. Prior to putting the EVAP system, the hydrocarbons evaporating from the fuel tank, from out of the float bowl, on the carburetor, all went to the atmosphere. When we added this system and started capturing those hydrocarbons and now burning them back through the engine, we reduced hydrocarbon emissions by another 20%. So just with the PCV system and with the EVAP system, we reduced hydrocarbons by 40%. Taking a look at our older system and the fuel tank, the hydrocarbons that are going to evaporate in there, we've sealed the cap. The hydrocarbons are going to come through this line into this charcoal canister. The charcoal canister is open at the bottom, but because of the activated charcoal inside there, it's actually going to grab a hold of the hydrocarbons, so it would be just air that got into the fuel tank that's going to come out here. We have another line that's coming up toward the car, and we come to this TVV, or thermostatic vacuum valve. You will find it on some vehicles as a TVS, thermostatic vacuum switch. This is going to be closed off while the engine is cold. Once the engine gets warmed up, this pathway is going to open up. This line will now be exposed to this port right here, which they refer to as ported vacuum. The throttle is closed. This is going to be exposed to atmosphere. It's not going to do anything. So it's not until we get the throttle open where we're going to be looking at a cruise condition. Now this will be exposed to vacuum. We're going to pull the hydrocarbons out of the charcoal canister, so air is now going to come in through this port down here. The air movement going through there is going to pick up the hydrocarbons. We're going to run the hydrocarbons into the intake manifold, run them through the engine, and burn them. This is referred to as purging. We are only going to purge the charcoal canister during cruise conditions when the engine is warmed up. TVS or TVV is what's going to prevent it from happening on a cold engine. Ported vacuum is what's going to prevent it from happening when the engine is at idle. Prior to putting the EVAP system on there, our fuel cap, which looked typically like this, was pretty much just a dust seal. Now we've got this cap over here that is going to seal up the system. However, if you look at this image over here, you'll see that there's actually quite a bit inside of here. This is only going to allow 2 psi to build up, and then it's going to vent. Because we have this open through here, pressure should never build up inside of there. Square inches that are on here, if you pulled this into a vacuum, you would actually crush down your fuel tank. The vacuum is typically only going to be allowed to go to about a half a psi, and it's not going to allow more than about 2 psi pressure to build up. Taking a look at another system on here, doing the same thing. So this one has our PCV system on here, which we're going to be pulling the hydrocarbons out of the fuel tank, capturing those. And this is tied into that same vacuum line, but this valve right here is going to prevent this from opening up inside of here. So we have our fuel tank, we have this line coming up to the charcoal canister. This is exposed to the atmosphere. We're also going to capture the fuel from the float bowl. Here is our ported vacuum, and this one doesn't show the thermostatic vacuum valve, or TVS. When you open the throttle, this is going to act as a signal. It's going to put a little bit of vacuum here. This is going to open up this passageway, and now air can come in, and we're going to burn those hydrocarbons. So a little bit different image of the same thing. Here's a picture of your charcoal canister. You see we've got multiple lines connected up here, and this has our multiple lines right there. This is the one that went to this signal line right there. During the early days, this charcoal canister was almost always up under the hood, and we had this line coming from the fuel tank clear up to the front of the vehicle. This charcoal canister here is what you're going to see on the newer vehicles. This is now going to almost always be located right next to the fuel tank, and you'll see that this fitting is actually much bigger than that fitting there. The reason for this larger fitting and moving the charcoal canister next to the fuel tank, as well as being a much larger, it is actually 2, 3, or even 4 times the size of the early ones, is we now have the onboard vapor recovery. And what that's going to do, while you're putting gas into your fuel tank, this is filling up with liquid, the hydrocarbons are now going to be forced through here into the charcoal canister. So we're capturing a lot more hydrocarbons with this system than what we used to do. Here's our old system again, so we look at this, and here's our new system. This one is 96 and newer. So OBD2 affected our evaporative emission system, and what they discovered is that a lot of evap systems were not doing their job, so the manufacturers now have to monitor the evap system. Same fuel tank that we had before, we have this line coming over here to our charcoal canister. Now, instead of being open on the bottom, we have this line coming over here, and we have this vent valve, which is normally open. Instead of a TVS and ported vacuum, what we now have is a purge solenoid. Purge solenoids can be controlled by the computer. This one is showing a flow sensor. Not all systems have a flow sensor, so we're going to ignore that one. There is now a fuel tank pressure sensor that the computer is going to monitor. The fuel level, which we've always had for the gauge, well, always, starting from the 40s forward, instead of the fuel level sending unit going to the gauge on the dash, it now goes to the PCM, or the engine computer. Each time that you start the vehicle up and run it, the computer is going to try to run a test on this system. Now, the reason I say try is because unless it is a cold start, it's not going to run the test. Start the vehicle up cold. When the computers run some other tests, it's now going to come over and run this test. And what it's going to do, it's going to energize the vent solenoid, which means the vent solenoid is closed. It's going to energize the purge solenoid, which means the purge solenoid is now open. Vacuum is going to be applied. Because this is sealed up now, it's going to pull the fuel tank into a vacuum. Just a little bit of vacuum. We're going to be measuring this in inches of water, not inches of mercury. This sensor is going to tell the computer when the system went into a vacuum. The reason the computer is going to watch the fuel level is because how big this space is, whether the tank is full or close to empty, is going to affect how long it'll take to pull into a vacuum. The computer is going to look at temperature, it's going to look at the vacuum, it's going to look at the amount of time. Once the system pulls into a vacuum, the computer is going to say, okay, that test passed. Then the computer is going to close the purge solenoid. We now have the system sealed up. The computer is going to watch this vacuum to see if the system will hold the vacuum. As long as this holds the vacuum, the computer is happy, the system has maintained its integrity, it passed the test. Showing you up here, this is a picture of a vent solenoid, these typically ones that I've seen. And this is a picture of the purge solenoid that you're going to find up very close to the intake. The OBD2 diagnostics, the large leak, when the system goes to pull it into a vacuum, if it can't pull it into a vacuum, it's going to set a code or a DTC for a large leak. If it passes the test, so it does pull into a vacuum, then while it's trying to hold the vacuum, if it won't hold the vacuum, then it's going to set a code for a small leak. The onboard vapor recovery system, we talked about that. Some of the manufacturers, instead of having this vent solenoid like this, they have a air pump on there that they will use the air pump either to pressurize the fuel tank and run the same type of test, or they'll use this air pump to pull the system into a vacuum. So same basic thing, but a little more complicated using the air pump. As the emissions laws have gotten tighter, they have a smaller leak that they have to be able to find now. Some of the manufacturers are starting to use what they call a key-off natural vacuum test. While you're driving the vehicle reaches temperature, heat from the exhaust, heat from the road, this fuel tank's going to warm up. When you shut the key off, the computer is going to energize the vent solenoid, meaning it's closed, so the system is now sealed. As the fuel inside of here cools off, it wants to see the system pull into a vacuum. This is supposed to be able to detect a smaller leak. Some of the other changes to help with emissions, they've redesigned the cylinder. Piston rings are now higher up to reduce the quench area. redesigned the head, all of this to try to make the engine run cleaner, reducing both HC and CO emissions. The valve and intake system was redesigned to create more turbulence inside the cylinder, or a swirl effect. Again, the more turbulence there is, the hydrocarbons are going to stay mixed up and not want to stick to the walls, reducing our hydrocarbon emissions. They've improved the design of the head, the cooling system, to reduce hot spots. If you reduce the hot spots, you reduce the NOx emissions and the tendency for the engine to detonate or pre-ignition. Next emission item we're going to look at is the EGR valve. I do want to stress to you now, not all engines have an EGR valve. And we'll talk about that again later. This is our early EGR system. The EGR valves look like this. Diaphragm inside of here, they're going to apply vacuum. Atmospheric pressure pushing against a spring inside there is going to open this passageway, so there's a pintle inside there that's going to lift up. And intake manifold over here, exhaust over here, and we're going to run the exhaust. Image over here showing you that we have this exhaust passageway. It's going to come up when the EGR valve opens. We're going to put the exhaust into the intake. Purpose of this is to control NOx emissions, which if you just think about it logically, that instead of taking in cool outside air, we're going to bring in hot exhaust. And that's going to help cool the combustion process. Now what it's really doing is it's displacing some of the air coming in with an inert gas. If they put in a 10% inert gas, they're going to reduce the fuel by 10%. And what this means is we now have 10% less air fuel in the cylinder. We don't have as much to burn. It won't burn as hot. The way we're going to control the EGR valve is literally the same way they controlled the evap system on your early vehicles. We have our TVV or TVS, and here's an image of one. This is going to be closed off. We don't want EGR. We don't need EGR if the engine's cold. We're not going to have any detonation, pre-ignition. NOx emissions are going to be low. This P right here is for ported vacuum. The M is the manifold vacuum. This would be the base of your carburetor. Open the throttle up, so we're getting into a cruise condition. Now we're going to put vacuum here. Engine's warmed up. We're going to allow that vacuum to come over here. Start to open up the EGR valve. Same way that we purged hot in cruise, we're going to open the EGR valve up during hot and cruise. On the later systems, now we went to computer controlled of the EGR system. So I tried to draw this out over here. Try to follow along with what I'm talking about here because this can become critical. This is now by the EGR valve. And here's your EGR solenoid. You'll see this cap looking piece right here. Underneath this cap is a filter. And that's what I took a picture of a filter, put it right there. Here's our solenoid. As the solenoid opens up, vacuum is now going to be applied to this chamber. If we didn't have this bleed right here, if we just have a sealed up system, we open it up, a little bit of vacuum, open it again, a little bit more. As you keep opening it, vacuum's going to go higher and higher, and the EGR valve is going to be all the way open. What's actually going to happen, this solenoid is going to be duty cycle controlled. So, opening and closing, they're going to vary the duty cycle. What is going to happen is, when it's open, we're applying vacuum. When it's closed, we're going to bleed off the vacuum that's being applied to the EGR valve. So the unique thing about the EGR solenoid is it has this bleed that's on there. Increase the duty cycle, you increase the amount of time the vacuum's applied, means you're going to apply more vacuum, open the EGR valve a little bit farther, change the engine load, change the RPM. They decrease the duty cycle to decrease the vacuum. It gives the computer precise control of how far the EGR valve is open. If this filter inside of here gets plugged, what that means is shortly after starting the car, it's going to apply full vacuum to the EGR valve. The EGR valve is going to be all the way open, and it's going to cause your car to stumble, run rough, misfires, or even die at idle. And People will say, oh, the EGR is stuck open, and they'll want to replace the EGR valve. It's actually this screen or this filter that got dirty inside of there. On the newer vehicles now, the EGR valve has become a single solenoid. GM used this 3-solenoid system for a short time in the early 90s. And what they had was 3 different size openings on the bottom here to control the amount of EGR. They then went to this about the time the rest of the industry did. So no more vacuum controlled. This large solenoid is going to be duty cycle controlled, but it's such a large solenoid it can't open and close very quickly. As they increase the duty cycle, it's going to be just like increasing the voltage to the solenoid, and the solenoid will start opening up farther and farther as you increase the voltage. In this top part right here, there is a pintle position sensor, a potentiometer, just like your throttle position sensor. Computer can look here and see how far it's opened up. If the computer is going to command it to be 25% open, this sensor is going to say, hey, you're 27% open. It'll decrease the duty cycle in order to open up just the amount that it wants to. Looking at this image over here, this coil right there, that's going to be this large electromagnet or solenoid. And here's our 3-wire potentiometer. Going back to the earlier system, prior to this solenoid right here, manufacturers used a back pressure transducer. So if you're working on an older vehicle, still has a vacuum controlled, here's our vacuum controlled EGR right here. And then this is our back pressure transducer. 3 lines right there. One is going to come from the solenoid. On the earlier systems, even without a solenoid, this would come from your ported vacuum. This is going to the EGR. This one right here actually had what looked like a vacuum line, but it went to the exhaust system. What's going to happen is, each time an exhaust valve opens up, there's a pressure pulse. The piston is pushing the exhaust out of there, and then the valve slams shut. That hot exhaust gas starts moving through there, leaving a low pressure area behind it until the next cylinder has an exhaust stroke. This is looking at those high-low pressures, and what it's going to do, it has a little bleed inside of here that, depending on the pressure changes, it'll either seal it or bleed it off. So they're using this for more precise control of the EGR valve. Domestic manufacturers actually had this built into the EGR valve. Asian manufacturers, this is typically where you'd see when you're testing this system, it becomes a little more complicated. You really need to look at the service manual. This system here is Ford only. Ford called this their Delta Pressure Feedback EGR or DPFE sensor. This is what the sensor looked like. You'll find these either in plastic or in aluminum, and you can't mix them up because they worked differently inside. These 2 ports that are coming off of here had, again, what looked like vacuum lines, but they came to this exhaust passageway between the exhaust and the EGR valve. There's a restriction right inside of here. If there's no flow, there's the same pressure on each side. Have a little bit of flow, you'll have a little bit of pressure drop. As the flow increases, there'll be a greater pressure drop. Ford is the only manufacturer that ever measured EGR flow. All the rest of the manufacturers calculate EGR flow. If you talk to a Ford mechanic that's worked on these systems, what you'll find is, yes, they get DPFE codes. However, most of the time you get a DPFE code, it's the DPFE sensor that's gone bad, not something else on the system. EGR problems. First of all, take a look. Here's our EGR valve right here. There's a passageway coming up from the exhaust, and this is going to go into the intake. So there's a passageway that comes right through here, and then it came down around here, and this 2 spots right here is where they actually fed the exhaust into the intake. Throttle body goes on here. As the air is coming in through the throttle body, the exhaust will be coming through there, and they're hoping that the exhaust will get mixed up so all the cylinders will get the same amount. All cylinders didn't get the same amount. But what the manufacturer was trying to do is make sure that we get enough in there, they lower NOx emissions and meet the federal emission standards or California emission standards. You can see from looking at this passageway is completely plugged off. There's a DTC for the 96 and newer vehicles, which is the P0401. This is what your P0401 is almost all the time. This needs to be cleaned out. Number of ways to clean it out. You can get a pick in there, you can pick it out. Some guys will tank it to try to get it cleaned out, but you got to get that carbon cleaned out so the passageway is opened up. This one right here, picking on Ford again, I was able to find these pictures. Ford is not the only manufacturer that has this problem. It's just this is the one that I could find the images for. What they've done is inside of the intake manifold, which is what you're looking at here, there is a second manifold inside of here, and this is an EGR manifold. So they have an EGR passage, and then they have these small holes right here, which feeds the exhaust to each cylinder. By doing it this way, each cylinder gets the same amount of EGR, much more precise control. What you can see here is all of these are plugged up. The other thing that can happen with this is if you had 5 of these plugged up, one was still open, that means when the EGR valve opens, that one cylinder gets all of the exhaust gas to it, and you end up with misfires. So you can have a P0304 misfire on one particular cylinder, and it's actually this EGR passageway that's plugged up. Just for a comparison, here's a brand new one. Figure out a way to clean the carbon out of there. You can use some decarboning agent, some Easy Off oven cleaner can clean it out, but you got to be careful because Easy Off oven cleaner is hard on aluminum. I've heard of guys using a torch to burn the carbon out of there. I'm not brave enough to do that. The carbon is going to build up where the exhaust cools at. Most all the time, your carboned up passageway is going to be between the EGR valve and the intake. We talked about not all engines have an EGR system. Look at the emission sticker. If this vehicle has a EGR, it'll list it on there. Excessive valve overlap, that's going to create a similar effect to the EGR. With our variable valve timing now, they can change the valve opening. So you have very little valve overlap at low RPM. As RPM increases, increase the amount of valve overlap. Engine can get more power, and they can reduce the need for the EGR valve. Next emission item is going to be our catalytic converter. Looking at this cat down here, this is the front. This one's the back. You can tell because we have this oxygen sensor behind the catalytic converter that's going to be used for monitoring catalyst efficiency. As you look inside of this, we have one catalyst here, we have a second catalyst here. By seeing the 2 different catalysts, I know now that this is a 3-way catalytic converter. With a 3-way catalytic converter, we're going to convert HC, CO, and NOx. If we have an oxidation converter, it does not have the ability to convert NOx. This first catalyst is for converting NOx. It wouldn't have this one, it just has this second catalyst. So this first one is rhodium. Rhodium is going to cause a chemical change to happen. As the NOx is exposed to the rhodium inside of there, it is going to split the nitrogen and oxygen, and we're going to have just nitrogen, or the N2, and O2 that's going to pass through there. That is the reason that the first catalyst is always going to be your rhodium, is because it's going to provide additional oxygen for your second catalyst. Our second catalyst is going to be platinum and palladium. The platinum and palladium is going to split the hydrocarbon or combine it with oxygen, and we're going to end up with H2O and CO2. The CO that comes into there, it's going to add an additional oxygen molecule. If we had a perfect world, there would be no NOx, no HC, no CO. It would just be the CO2, nitrogen coming out of the catalytic converter. One other chemical that's inside of there is the second catalyst also has cerium. And what cerium does is it gives the catalytic converter the ability to store oxygen. while you're driving along, the oxygen sensor is constantly going rich, lean, rich, lean, rich, lean, back and forth. When it goes lean, it gives the catalytic converter additional oxygen. If you start climbing up a hill or you start pushing the vehicle hard, we're going to go into a fuel enrichment mode. Now we're going to be having more HC. If the catalytic converter did not have the ability to store the oxygen, within a few seconds, the catalytic converter would not be able to do its job. Secondary air system. Very few vehicles have secondary air. So domestic manufacturers here in the US, Asian manufacturers are only going to put a secondary air pump on their car if that's what they have to do in order to meet emissions. Volkswagen is going to put secondary air on just about everything that they make. So depending on what you work on is whether you're going to see very much of these secondary air systems. What they're going to do is pump air into the exhaust, and it would seem like at first that, hey, all we're doing is diluting the exhaust, but now it's not actually doing that. When the exhaust valve opens up, that air-fuel mixture is still hot enough to burn. If we can pump some air into the exhaust, it'll finish the burn in the exhaust. And that is going to consume the hydrocarbons, so we will lower hydrocarbon emissions. Now, a lot of the stuff that I read says that this will also lower CO. I have a hard time believing that if I formed CO in the combustion chamber, just shooting air at it, I'm not convinced that that's going to convert CO. The other thing, as you pump the air into the exhaust and we finish the burn in the exhaust, we're going to heat up the oxygen sensor quicker. We're going to heat up the catalytic converter. This is a really good system, but it's a bit expensive, so the manufacturers, except for Volkswagen, don't like to put it on there. The air can be pumped upstream into the exhaust manifold, which is what I was talking about. On the older system, they also pumped it downstream into the catalytic converter. So they're going to pump it into the middle of the catalytic converter because our first part of the cat, the rhodium, didn't need additional oxygen. But pumping air into the catalytic converter will improve the efficiency of your cat. Upstream during cold start, downstream once the system goes closed loop. During deceleration, if you pump air into the exhaust, the engine's going to backfire. That's a given. Most of the systems that are out there now, you're going to see an electric air pump, and they're just going to be upstream. Here's our early system. We had a secondary air manifold. Screwed onto the secondary air manifold are these check valves, and all these secondary air systems have a check valve because we don't want the exhaust coming back into our control valve. Here is our control valve, which you can see there's vacuum on here, and you really can't see it very well, but there's a solenoid here and a solenoid here. So this is electrically controlled, at least on the early ones prior to the engine computer. Once we had the engine computer on there, then these were electronically controlled by the computer. But these two solenoids are going to direct it either upstream into the exhaust manifold, downstream into the catalytic converter, which there will be another check valve down here, or dump it during deceleration. Now, this air pump was kind of noisy, so when it dumped it into some sort of muffler or into the air cleaner. Belt-driven air pump, so if the engine's running, this is pumping air. This really didn't affect fuel mileage. This is a low-pressure pump, so we're talking about a couple PSI and a low volume. It comes from here to our control valve, upstream, downstream, or down. Looking at our newer system here, we have our electric air pump. The electric air pump is going to pump it through the check valve into one manifold, through the check valve into the other manifold. With the electric air pump, here's what they typically look like. One's going to be an inlet, there's an outlet. From the outlet, it's going to come to the check valve. You can see the check valve has a vacuum line on there, so there's going to be a solenoid. And it's a computer that's going to open up the solenoid, or energize the solenoid, open up the valve, and allow the air to go into the exhaust manifold. This pump is only going to run for a few seconds. So if your engine's at 160 degrees or 150 degrees, this may only run for 5, 6, 7 seconds. And then it shuts off. The rest of the time it's along for the ride. If you're living up in Alaska and it's minus 40 outside, this may run for 2 minutes when you start the engine. Not a high failure On this system here, the ones that I've had to fix, on some of the GM systems, they actually scooped the air from down low. If you went through a puddle, it would get water inside here, then you park it overnight. The water that got inside there froze. Now when it starts up the next morning, it just shears the fan blade inside of there. I've had to replace a few of these on the GM. The other vehicles that I've worked on, it's this check valve that went bad when got a code for the secondary air pump. Ignition control, if you advance the timing, your fuel economy will improve and you'll get more horsepower. However, you're going to have higher hydrocarbon emissions and higher NOx emissions. Combustion temperatures will start getting hotter. So manufacturers are going to have computer control the timing in order to keep emissions low. Then they also have this NOx sensor. This is a couple different types of NOx sensors. Internally, they're the same. It's just different shapes. This one is actually going to screw into the block or into the head. This one has a bolt that's going to hold it down. And they'll have one or two wires coming to it. Most of them that I've seen are just a single wire. This is a piezo crystal inside of here that's going to vibrate with noise. The computer's going to look at the frequency and the amplitude of this signal coming from here and will retard the timing if it detects an engine knock. When the engine is knocking or pinging, whether it's pre-ignition or detonation, that's going to cause high NOx emissions as well as being really hard and dangerous for the engine. And that's it for this one. Hope you have a better understanding now of the emission items that are on the car and the emissions that we're trying to control.